So thank you very much for participating and for giving a talk to this great event. And please feel free to start whenever you are ready.
Thank you very much for your introduction. It is my great pleasure to give a talk at this international congress dedicated to Professor Kaufman on the occasion of his 80th birthday. And this is a joint work with Mikami Hirasawa and Ryota Hiura. Okay, so please allow me to begin my talk by explaining the benefits I have received from Professor Kaufman's paper. Okay, about 40 years ago, I had a chance to study his handwritten draft of a paper concerning state model of the Jones polynomials. And I was deeply impressed by the paper, by the theory, and realized that this theory should be used to solve a question proposed by Professor Murasugi in one of his talks. And then I wrote this paper. So you can find Murasugi and Kaufman. Okay. And thanks to this paper, Professor Murasugi kindly invited me to the University of Toronto from September 91 to May 92. So this was a very important time for me, and the researches that I carried out during that time laid the foundation of all of my future works. Okay. And actually, this work, one of the starting point of this work is this paper that is made in Toronto. And another starting point is this paper that was written precisely, that was published 40 years ago. And this paper attracted no attention for a while, but to my present surprise, it attracts many people start to interest in strongly invertible knots from the viewpoint of four-dimensional topology, and many people kindly mentioned to this paper. And today's talk is about strongly invertible knots from the three-dimensional viewpoint. Okay, so here's my plan, and my talk is about these papers. Okay, let K be a smooth knot in smooth-oriented knot in the C-sphere. Then K is said to be strongly invertible if there is a smooth orientation preserving involution of three-sphere, whose fixed point set is a circle intersecting K in 2 points. So it reverses the orientation of K. So H1 and H2. So they give strong invertibility of the knot K, and we call it the strong inversion. Okay, and another definition, a knot K is said to be periodic of period N if there is a smooth orientation preserving map of the three-sphere of period N, such that which preserves K, and the fixed point set is a circle disjoint from K. So it preserves K, preserving the orientation. So in this case, F is pi rotation around here. This gives a period 2 of this knot. Okay, so now I will give an example. Let KAB be the plumbing or Murasugi sum of unknotted twisted annuli, two unknotted annuli, and one is A full twist, the other is B full twist. So in this case, we have A full, maybe 2 full twist, and this is the other full twist. And so we have 2 strong inversions, and their product gives periodicity. Okay. Now, one of the starting point of this talk is this theorem due to Alan Edmonds. Okay, he has proved that every periodic knot admits an invariant Seifert surface of minimal genus. And by using this theorem, he proved the Fox conjecture, which says that every knot admits only finitely many periods. Okay. Then the following In this talk, I'd like to study the following very natural question. What happens for strongly invertible knots? Okay. Then I will study this example. Okay. Consider the previous example and apply the Seifert algorithm to this diagram. Then you have this Seifert circle and two bands. Okay. And finally, we need to add a disk to this circle. And we have two choices from the above or below of the projective plane. Okay. Then both surfaces, so I denote this surface F plus minus. Then the periodicity F preserves this surface because it preserves D plus minus. Okay, so this gives an example of Edmond's theorem. But for the inversion, strong inversion H, it interchanges D plus and D minus. So we have a trouble. Okay. And in fact, we can show that this knot does not admit an H invariant minimal genus surface. This can be seen as follows. By the work of Hatcher-Thurston or Kobayashi, the surfaces F plus minus are the only minimal genus surface for K up to isotropy preserving K. Moreover, they are not isotopic. Since the strong inversion interchanges F plus minus, F plus and F minus, no minimal genus surface is preserved by the strong inversion. Okay. So this is a motivating example. And this phenomena can be described nicely in terms of the Kakimi's complex. So the Kakimi's complex for oriented ring L is a flag simple complex constructed as follows. The vertex set is the isotopy classes of the minimal genus surface for L. And N plus 1 surfaces span an N simplex. If and only if we can find they are representative so that they intersect only along the boundary. So in the exterior, they are disjoint. So this is Kakimi's complex. And the Kakimi's complex of this knot is just consists of two vertices and one edge. And the strong inversion interchanges these points. Okay, so I'd like to formulate our questions as follows. First, does every strongly inverted knot admit an invariant surface? Okay, so by this reason, it's not obvious, trivial to find an invariant surface. And secondly, for a strongly invertible knot K, what does the action of a strong inversion of K on the Kakimi's complex look like? Okay. And finally, can we determine the genus of the can we determine the minimal genera of invariant surfaces of a given strongly invertible knot? And here's the answer which I described in this talk. For the first question, the answer is of course yes. And we have two proofs by Hura and Boyle and Issa. And for two, I will give some general result and a complete description for two bridge knots. And finally, for the third question, we give a complete answer for two bridge knot which extends Hura's previous result. Okay. So now I'd like to begin by explaining the construction of invariant surface. So in this talk, I mean by a strongly invertible knot, I mean a pair of a knot K and strong inversion H, and two strongly invertible knots are equivalent if there is a diffeomorphism between the pairs, which and by which H1 and H2 are conjugate. Okay, but we assume that it is orientation preserving. This phi preserves the orientation of 3. This is our equivalence. Okay, and here is some basic fact concerning strongly invertible knot. First, by the positive solution of the Smith conjecture, H is just a standard rotation. So the quotient of the 3-sphere by H is again the 3-sphere, and the quotient of fixed point H is a trivial knot. And the quotient of K is an arc which intersects the trivial knot O in 2 points. So we obtain the union of O and K hat gives a spatial curve of the theta curve, of the shape of theta curve. Okay? And secondly, if S is a H invariant surface for K, then the intersection delta of S and the fixed point set H is one of the sub-arcs of the fixed point set H bounded by K. Okay? And so if you take the quotient of S, then you obtain a compact surface S check bounded by the image K hat of K and the image delta hat of delta. And it intersects this knot O in precisely in this arc. This is very basic observation. And by using this observation, I need to prepare more notation. By a marked strong invertible knot, we mean a triple KH delta, where delta is a subarc of fixed point set bounded by the intersection with K. So delta is something like this. And by an invariant Seifert surface for this marked strongly invertible knot K, knot is an H invariant Seifert surface S for K, such that S intersection fixed point H is equal to this delta. And by the equivalent genus of this knot, we mean the minimum of such invariant Seifert surfaces. Okay, and Hewler and Boyle independently observed that every marked strongly invertible knot KH delta admits an invariant Seifert surface. So this genus is well defined. Okay, and I first explain Hewler's result construction. And this surface, this is the result constructed by using Hewler's algorithm. Here we use the fact that this processing, this part is isotoped to this one. And so if you consider this surface S, it is an invariant Seifert surface for this knot, and where delta is this arc. And this construction is based on the following basic fact. If you take the quotient of S and let S check, then it is a compact surface in the quotient space, which is bounded by K hat, bounded by the union of K check and delta check, and it intersects the trivial knot only in delta hat. And moreover, very important thing is that the fact that S is orientable implies that the homomorphism defined as follows. Namely, if you pick up the homology cycle, then consider the linking number of alpha and O. So consider linking number of alpha and O. Then it is equal to the orientation homeomorphism of S hat. So please note that S check is generically non-orientable. So it has an orientation homomorphism. And the key fact is that this homomorphism should be identical to this homomorphism. And conversely, any surface S check which satisfies this condition, lifts to an invariant Seifert surface. So Hibra gave an algorithm how to construct S-check. Okay. Now, but Boyle and Issa later gave a very clever construction. Instead of this diagram, namely, the fixed point set H is a line on the projection plane, we choose another projection where the axis is transversal to the projection plane. Okay, then just apply Dirichlet algorithm to this diagram. Then we automatically obtain an invariant Seifert surface. But this does not give, but we cannot nicely illustrate the surface by this construction. And here is, here I give Hirasawa's improvement of this algorithm. And you can see that in this case, the genus is equal to 1. And please note that, okay, the previous, we have, in this special case, we have every tubular knot has very natural two strong inversions. But in this particular case, because of the symmetry here, we have another strong inversion. And okay, this H prime is this H prime. And for this particular knot, KH1 and KH2 are equivalent, but they are not equivalent to KH prime. Okay, so this is two algorithms. Okay. Now, I'd like to give an analog of Edmond's theorem on periodic knots. So please recall that Edmond has shown that every periodic knot admits a minimal genus invariant surface. Okay, and here is the analog of Edmond's theorem for strongly invertible knot. For any strongly invertible knot KH, there is a minimal Seifert surface F for K such that F and its image by H intersects only along the knot K. So their interiors are disjoint. So here is a schematical picture. We have a strong inversion, then we can find a minimal Seifert surface, something like this. This is a picture of the exterior. Okay, and secondly, for this given for this much strong invertible knot and the surface F as in this proposition theorem, we can find a minimal genus invariant Seifert surface S for this marked strongly invertible knot, such that it is disjoint from these surfaces. So in other words, F and HF cut the exterior into two parts, and one of which contains arc delta, and the other contains the complementary arc. And if you stick to delta, then we can find invariant surface illustrated in this picture. And the proof of the first assertion is just an imitation of Edmond's argument using minimal surface theory. And the second part can be proved by equivariant cut and paste argument in the infinite cyclic covering. Okay. Now let me explain its corollary. Let KH be a strongly invertible knot, and let H star be the automorphism of the Kakimi's complex induced from H. Then one of the following holds. H star fixes a vertex of MSK, or H star acts on an edge of MSK as a reflection. So generically, we have this setting, but sometimes they can be equivalent. So these two surfaces can be isotopic in many cases. In that case, we obtain this picture. So in particular, H satisfies a vertex on an edge of MSL. Okay? And for a special Arbor-Center link L, namely a link obtained by successive plumbing of unknotted, non-trivially twisted annuli along planar tree. So in particular, every tubular knot satisfies this condition, then the Kakimi's complex is a triangulated cube or its linear quotient. So looks something like this. Okay, and we can prove that for a two-bridge knot K and its standard strong inversion, the fixed point set H star, a fixed point of H star is either a vertex or a midpoint of an edge of n scale. So we have, okay, here is a generic picture of the Kakimi's complex of two-bridge knots. So it is a triangulated cube, namely the underlying space is a cube and whose vertex set are the corners. So this is a generic picture, and the strong inversion is just an yes, reflection in this point. But sometimes the Kakimi's complex degenerate. Sometimes this direction degenerates. Then you obtain this picture. And sometimes this edge degenerates. Then you obtain this picture. And in this case, we have this picture. And if you if the degeneration occurs in two different places, then the Kakimi complex becomes a one-dimensional. The underlying space becomes one-dimensional, and finally it becomes a point. So in these cases, in this case, yes, in this case, in this case, the fixed point set is the vertex. And the other case, the fixed point set is an edge, is the central point of an edge. And for the exceptional involution H dash, we have this picture. So in this sense, we can completely understand the action of H star. Okay, this, and I think, okay, this corollary may be regarded as a refinement of the following more general result. Okay, but and instead of describing this result, I'd like to explain very important thing. Theorem proved by Pszczewski and Schultens. So Kakimi's has conjectured that the underlying space of MSL is contractible. And it has been a long-standing conjecture, and I could prove the conjecture only by very special cases. And but they have succeeded in proving that MSL is always contractible, and they obtain some corollary. And the previous result can be regarded as a refinement of this, of a special case of this theorem. Okay. 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 Now I move to the most important part. So I'd like to determine the equivalent genera for marked strongly invertible knots associated with two-bridge knots. Okay, so every two-bridge knot has the following expression. You can choose, there is even number of non-zero integers such that K is, that the two-bridge knot is a successive plumbing of A1 full-twisted bands, B1 full-twisted band, and so on. So this, for example, we have this, in this case, we have two full twists, three full twists, minus one full twist, and so on. Okay. And if for simplicity, we treat only in this case, namely n is equal to 1. So genus 1 two-bridge knot. And we also assume that AB is not equal to 1, 1, or minus 1, 1 minus 1. Because in this case, it is just a trefoil knot or its mirror image. And so it is not, for this case, we can easily understand everything. So we treat that our knot is not torus knot. So KAB is a genus 1 hyperbolic knot. And for this knot, we have the following classification of strong inversions. Okay, for the knot K in AB, we have the following result. K admits precisely two strong inversions up to equivalence. Okay? And generically, when A and B are different, this H1, H2 gives these two equivalent strong inversions. But in the exceptional case, A equal B, we have another strong inversion which interchanges this one and this one. Okay, and in this case, H1 and H2 are equivalent, and H prime are not equivalent to this guy. So these two strong inversions give us the only strong inversions for two-bridge knots in this case. Okay, and for each of the strong inversions, we have precisely two choices of the arcs, and actually they are different. So it follows that there are precisely four marked strong invertible knots with underlying knot K. Okay. And so we have four, but the strong inversion H2 for the knot KAB is equivalent to the strong inversion H1 for KBA. So if you interchange A and B, then H1 and H2 interchanges. And moreover, we have already observed through Hirasawa's observation, Hirasawa's construction, that for this exceptional involution, the equivalent genus is equal to the usual genus. So we have only to study this case. Namely, we consider the knot KAB, so A full twisted band and B full twisted band, they are plumbed together. And we stick to this strong inversion. Then we have two choices, tau and tau complement. We call tau the short tunnel, and tau C, tau complement, we call the long tunnel. Okay. Then we have the following result. The genus of KAB and with H for this short tunnel is equal to the absolute value of A. And in other words, this is the genus is equal to 1. So the genus plus absolute value A minus 1. Okay, this is the first result. And the second result is the following. For the longer tunnel, the genus, the equivalent genus is equal to 1 or 2. According to Feather, the absolute value is equal to 1 or greater than or equal to 2. So, and I'd like to, and since we don't have enough time, I give only the proof of this first statement. Okay, and okay, so we have already observed that by Fibula's construction, we have this dipole surface, and you can easily observe that this surface has genus absolute value A. So we have only to show the converse inequality. Okay. To this end, we consider the two minimal dipole surfaces which I previously explained. Namely, apply the Seifert algorithm, and you obtain these two bands and attach a disk from the above or below. So we have two dipole surfaces. Then after an isotopy, which we may assume that H interchanges H plus and H minus, and they intersect only along their boundary. And moreover, the union of these surfaces separates the slit sphere into two H-invariant handle bodies, M tau and M tau complement, where M tau contains tau. So here's a picture. So this picture is produced as follows. Consider a 3 ball, okay, and drill a hole and attach one handle. So this is our surface, and actually, and the knot lies on this surface, and this knot divides this surface into F plus and F minus. Okay, and by theorem A, analogy of analog of Edmond's theorem, we can find an H-invariant Seifert surface S for this knot, KH tau, realizing the genus, and properly embedded in this handle body. So we have only to study the surface in this handle body. Now, in order to study such a surface, we consider the disk here, namely H-invariant disk, which intersects the fixed point only along the arc tau. Okay. Now, then after an H-equivalent surgery, we may assume that our surface S intersects delta precisely along this arc tau. So we can cut along this space by delta. So let M and S0 be the pair obtained from this original pair by cutting along delta. So cut and shrink, then you obtain this picture. And S0 is the resulting surface. And let gamma be the boundary of the resulting surface. So we have some surface here and some invariants. So here, so we have some H invariant Seifert surface here whose boundary is gamma. Okay. Then we have the following. We can prove the following lemma: the first Betti number of S0 is greater than or equal to this quantity. Then, since S is obtained by identifying this part, the Betti number of S is bounded by this quantity, and which in turn implies that this estimate of the equivalent genus, and we obtain the theorem. So we have only to prove this one. And the proof is very simple. Okay, just take the quotient. So let's consider the triple M, S, and gamma, and consider the quotient by H. And we call them by M check, S0 check, and gamma check. Then M check is this, just this one. So 3 ball with 1 tunnel, namely it's a solid torus. And S0 check is some compact surface. And the gamma check is this arc. Okay. So so M check is homomorphic to S1 times disk. Okay. And gamma check is a simple loop on the boundary of this solid torus whose homology class is equal to 8 times S1 plus 1 times the boundary of the disk, namely meridian. And our surface, F check, is bounded by gamma check. And by using this fact, we can easily see that our Betti number is greater than or equal to the absolute value A. And since F is essentially double covering, we have this inequality. So this completes the proof of the lemma and also the theorem. I note that the surface F check is actually constructed as follows. Consider a disk here and join them by a tube. This is actually F check. And if you consider the inverse image, then you actually obtain this surface. Okay. And for other longer tunnel, we may similar argument works, but here we choose this disk and cut along this disk. Okay. Okay, here's a general theorem. For generically, we have this identity, and also this one. So as a corollary, we can say that we can obtain the following. GK and the equivalent, the genus and the equivalent genus are totally independent, except for the natural relations that, of course, the genus is at most the equivalent genus. Secondly, if the genus is zero, namely K is a trivial knot, then Marmot's theorem says that the equivalent genus is zero. So except for this one, they are totally independent in the sense that for any pair of possible integers satisfies this condition, we can find a marked strongly invertible knot, such that they are the genus and the equivalent genus. And also another corollary is what happens for the reference choices of delta and delta check. Then they can be arbitrary. It is our corollary. So we have obtained the complete answer for two-bridge knots. And finally, I'd like to talk about some questions. First, I'd like to ask if there is a three-dimensional algebraic invariant of marked strongly invertible knot that gives an effective estimate of the I equivalent genus, in particular, which recovers our theorem. I ask this question because the classical theorem by Murasugi and Crowell says that the genus of a alternating knot is determined by the Alexander polynomial, and more generally by the deep theorem by Osbach and Szabo, we know that the genus of a knot is determined by the Hegardt-Freyer homology. So for the standard genus, we are determined by an algebraic invariant. And my question is, what happens for the equivalent genus? Okay, and other remark is there is some invariant, but that is an equivariant coordinate invariant. So it cannot detect the theorem B tilde. And some related theorem by Duplessis and Flamber says that for every two-bridge knot K, this knot has an infinite order in the equivalent cobordism group. And the equivalent cobordism group is very interesting, and it is proved by Duplessis that is non-commutative. So we have many interesting questions in this direction. And back to the three dimension, I just point out that if K is fibered, then the equivalent genus is equal to G. And this is a consequence of Trefson. And a composite theory of divides says that if you have a divide, namely generic immersion of the interval to the disk, then we obtain a strongly invertible fibered knot. And his theory gives a very nice, beautiful description of the two invariant Seifert fiber surfaces. And the question proposed by Acampo is the following. So Culture has shown that every strongly inverted knot is represented by a signed divide. And also this was simplified by Sugawara into divide with cusps. So in this case, we have a figure knot. So what happens? Can we study this strong equivalent genus from this viewpoint? I think this is a very interesting project. And finally, please allow me to end my talk by showing you the emails which I have just received the day before yesterday and yesterday from Julian Marche. He asked a question about two-bridge knot to me. He asked that question because he says that strong inversions of two-bridge knots are useful in the studies of torsions and signatures of TQFT. I know no knowledge about TQFT, but I'm very glad to hear that the two-bridge knot and its strong inversions are related to TQFT. And finally, this theory is motivated. Of course, you can find the name of Kaufman. So thank you very much. That is all of my talk. Thank you.